Hello everyone, I'm going to go ahead and work number 97 from the book. This is a fairly complex problem. It's going to take lots of steps. We're going to use a couple different laws. Okay, a 25 gram ball is fired with an initial horizontal velocity towards a 125 gram ball that's hanging motionless from a 1.25 meter long string. They have a perfectly elastic collision, and as a result the second ball swings out 37 degrees from vertical. Determine the initial velocity of the ball. Nice spelling. Alright. So we have a lot of information, and there's actually two events in this picture, and we need to be able to separate them. Okay? Two events means three different scenarios. So there's a before and an after and another after. Let's start with my before and my first event. So the first event is a collision. Okay? And then there's an after the collision. But then I have a second event. The second event is the swing. Okay? So I have an after the swing as well. So that means when I start to organize all this information, I actually have three pictures of information that I'm going to try to organize. Okay? So let's go to the after picture. Okay? What I know is at the end it says the hanging ball swings out 37 degrees from vertical. So the hanging ball used to be way down here, and it got hit and it swung up to here, and this is 37 degrees. I know that this distance is 1.25 meters. The string didn't get longer or shorter, so this is still 1.25 meters. It's just a very poor picture. That's what I know after the swing, after everything has happened. Now, before the swing, what did we have? Well, let's go actually to our initial, before anything happened. Before anything happened, we have a ball hanging here. This is ball A, or ball B, sorry. This is B in both pictures. And we had ball A that's moving this way. And it's got some velocity. I'm going to call it VA naught. That's the initial velocity of object A. That's actually what the whole problem is asking us to find. Determine the initial velocity of the ball. It's moving this direction. We know its mass, 0.025 kilograms. We also know the mass of ball B. It's 0.125 kilograms. So this is before the collision. After the collision, and this I'm talking immediately after the collision, so the ball hasn't started to swing yet, these two things basically just hit. Perfectly elastic collision. This ball B is going to be moving this direction with some velocity V. I'm going to call it VB. Ball A is also going to be moving. It's going to have some velocity. I don't know what it is, but it hit that ball. So I'm going to draw it this way for now, and I'm going to call it VA. Okay, this is VA, not VA naught, because this is initial, this is final, or at least one of the finals. Now, the reason I have to have two different events and two different collisions and stuff is because there's different laws I can use at different times. Okay, before the collision to after the collision, this is a closed system because I'm looking immediately after, which means this thing is just moving, and the two forces, the force from the string and the force from gravity, are balanced, so they cancel each other. And that means this is a closed, isolated system, and I can use the law of conservation of momentum. So by choosing it that way, over here I have conservation of momentum. Momentum is conserved. However, I also know one more thing over here. Because this is a perfectly elastic collision, I also know kinetic energy is conserved. But it's only conserved from immediately before the collision to immediately after the collision. It's not conserved over here where we get the swing. So on this side, it includes this event to here, and it includes the swing as my event. This one, I don't have momentum conserved, I don't have kinetic energy conserved, but I do have mechanical energy is conserved. Okay? Mechanical energy is always conserved, at least if friction is not involved. So in an inelastic collision, you have things that are absorbing those and changing that energy from mechanical into something else. But in a pendulum swing, we don't have to deal with that. So the mechanical energy is conserved over on this side of it. And this side of it is actually where I want to start, because this is where I know the most information about this problem. I know the mass of this ball, m equals 0.125 kilograms. and I know how far it's swung, and there's nothing else in this picture to know about. So what I know is the potential energy up here at the top of its swing is equal to the kinetic energy it started with down here at the bottom of its swing, because gravity just changed that kinetic energy into potential as it swung up. So its potential energy is equal to m times g times h. But I know enough information to get all of that. Okay? I need h, which is how high it goes above its low point. That would be this distance here. Okay? I know the hypotenuse of this triangle, so I can find this side. Right? H plus x has to give me the whole thing, so h plus x equals 1.25 meters, and x, this part of this triangle, is just 1.25 times the cosine of 37. So 1.25 cosine 37 is equal to 0.998, or close enough, yeah, I'll call it 0.998, which means h is 1.25 minus that, which is 0.2517. We'll call it 0.252 meters, which means I can get mgh. The potential energy of this ball is 0.125, its mass, times the acceleration due to gravity, 9.8, times the initial height, or sorry, the final height, 0.252 meters. So 0.252 times 9.8 times 0.125 is 0.3087 joules. That's how much potential energy this thing started with, which means, or ended with. That's how much kinetic energy that it actually started with. So kinetic energy is equal to 1/2 mass times velocity squared is equal to 0.3087. So I'm going to go ahead, and I know the mass, so I have 1/2 0.125 v squared, and this v, I should tell you, this is VB. This is the velocity of the ball right after it started to swing. So VB, VB squared equals 0.3087. And if we go ahead and do the math there, half of 0.125, and then we take 0.3087, 0.3087 divided by that gets us 4.939. So v, the velocity of b squared, equals 4.9392, and square root that, and we get 2.22 meters per second. This is the velocity of ball B immediately after the collision. Now, I'm working this problem backwards because that's where I had the most information, but I just was able to fill in some more information here. 2.22 meters per second. So now I know how fast this ball is going immediately after the collision, and that is going to get me what I need. Because remember, I have momentum and kinetic energy conserved between these two collisions or events or processes. So let's go ahead and switch to a different color. We're going to go with green, and green will be our conservation of momentum color. Okay? So momentum. And just like before, we have to have our initial and our final. Alright, so initially I have object A with some velocity VA naught, and that's what I want to know. So VA naught times its mass, 0.025, plus 0, because this object, object B, is at rest, it has no momentum, is equal to the total momentum afterwards, which is going to be VA times 0.025 plus VB, which I know, 2.22, times its mass, 0.125. Okay? So that's the momentum of the system before and the momentum of the system after. Okay? Now, these are two different things. This is VA and this is VA naught, so I can't combine those, but I can simplify a little bit. So 0.025 VA naught equals 0.025 VA plus 2.22 times 0.125, which turns out to be 0.2778. 0.2778. Okay? So here's an equation, and if I could solve it, I'd be done. But I can't solve it. There's two unknowns. I don't know initial velocity or final velocity. So I need a second equation. So now we're going to switch to kinetic energy. I'm going to put kinetic energy in red. And what I know about this thing in terms of energy, I do know kinetic energy is conserved since it's a perfectly elastic collision. So that tells me 1/2 the mass, 0.025, times the velocity of the object at the beginning, VA naught, squared, plus the kinetic energy of the second object, which is just 0, equals the kinetic energy immediately after the collision. So that's 1/2 0.025 VA squared plus 1/2 0.125 VB, which I know is right here, 2.22 squared. Okay? Actually, I know the kinetic energy is going to be 0.3087, but that's okay. We'll go ahead and do some math. So we're going to simplify this a little bit. 0.0125 VA naught squared equals 0.0125 VA squared plus 1/2 0.5 times 0.125 times 2.22 squared, and that gets me my 0.308, just like I knew that it should. Okay, so plus 0.3087, and now I have a second equation. Okay? So two equations, two unknowns. I need to solve one for the other and substitute it in. Either that or I'm going to have to do some other form of simultaneous equation solving. This equation, this green one, looks like it'll be the easiest one to deal with because there's no squares in it. And in fact, I'm just one division away from solving it for VA naught. So I'm going to go ahead and solve this one for VA naught real quick by dividing everything by 0.025. So VA naught equals VA, because 0.025 divided by 0.025 is 1, plus 0.2778 divided by 0.025 is 11.111. So plus 11.112. Now I have a second equation to use in here. I can replace VA naught with VA plus 11.112. And at the end I'm going to have to come back and make that substitution again. That's okay. So 0.0125, if I wanted to, I could clean this whole thing up right now and divide by this 0.0125. Why don't I do that? Okay. So before I make the substitution, I'm going to go ahead and divide everything by this 0.0125. So I have VA naught squared equals VA squared plus 0.3087 divided by 0.0125 is 24.696. Alright, now I'm going to go ahead and I'm going to make this substitution into this equation. So VA naught equals VA plus 11.112, remember this whole quantity is squared, equals VA squared plus 24.696. Alright, so this thing squared, I've got to go ahead and factor or FOIL that out. So VA squared plus 11.12 times 2, 22.224 VA plus 11.112 squared, 123.48, 4766 equals VA squared plus 24.696. Now this is nice because I'm going to subtract off this VA squared and it goes away, so all of a sudden it's not a quadratic anymore, it's just a linear equation. And let's see, I can subtract over this 123.4766, so I have 22.224 VA equals 24.696 minus 123.4766 is negative 98.6 0.7806, divide that by the 22.224, and I get -4. So the velocity of ball A immediately after the collision is -4.44 meters per second. This is not the answer that I want. This tells me this velocity right here. It turned out it's bounced back 4.44 meters per second. However, I'm almost done because all I have to do is plug it into this equation here and I've got the answer. So plus 11.112, and I get 6.67 meters per second. So VA naught is 6.67 meters per second. Okay. Yes, it's a long problem, but you're just using all the conservation laws appropriately in order to solve for it.